Section 11 of the Science, History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Owen Patrick. The Science, History of the Universe, Volume 2. Edited by Francis Rolt Wheeler. Geology. Chapter 6. Composition of the Earth, Part 1. A discussion of the geological changes which this planet has undergone ought to be preceded by a study of the materials which enter into its composition. This branch of geology is technically termed geognosy. The Earth may be considered as a globe, which has cooled sufficiently to have a solid crust, enclosed in two envelopes or shells, the inner one of water covering about 3/4 of the globe, and the outer one of gas completely enveloping the whole. This outer envelope of gas is known as the atmosphere. The water is called the hydrosphere, and the solid globe is the lithosphere, or rock sphere. There is every reason to believe that the present gaseous and liquid envelopes of the planet are only a portion of the original mass of gas and water with which the globe was invested. As Sir Archibald Geikie says in his textbook of geology, fully a half of the outer shell or crust of the Earth consists of oxygen, which probably once existed in the primeval atmosphere. The extent, likewise, to which water has been abstracted by materials is almost incredible. It has been estimated that already 1/3 of the whole mass of the ocean has been thus absorbed. Eventually, the condition of the planet will probably resemble that of the Moon, a globe without air or water or life of any kind. The gaseous envelope to which the name of atmosphere is given extends from the Earth's surface to a distance which has been variously estimated according to the methods of observation employed. From the phenomena of twilight, it may be inferred that the atmosphere must be at least 45 miles thick. The aurora indicates a sensible atmosphere at 100 miles, and clouds have been detected at heights of nearly 100 miles. Meteorites, which become incandescent by friction against our atmosphere, sometimes appear at heights of 150 miles. We may therefore infer that the atmosphere stretches for at least that distance from the Earth's surface, and probably in a state of extreme tenuity much farther. At sea level, the mean pressure of the atmosphere is about 14¾ pounds per square inch. Many speculations have been made regarding the chemical composition of the atmosphere during former geological periods. There can indeed be no doubt that it must originally have differed very greatly from its present condition. It has been contended, for instance, that originally there was little or no free oxygen in the atmosphere, which may have consisted mainly of nitrogen, carbonic acid, and aqueous vapor. Besides the abstraction of the oxygen, which now forms fully a half of the outer crust of the Earth, the vast beds of coal found all over the world in geological formations of many different ages doubtless represent so much carbon dioxide, carbonic acid, once present in the air. As now existing, the atmosphere is considered to be normally a mechanical mixture of nearly 4 volumes of nitrogen and 1 of oxygen, with minute proportions of carbon dioxide and water vapor and still smaller quantities of ammonia and the powerful oxidizing agent, ozone. The mean proportion of carbon dioxide is about 3.5 parts in every 10,000 of air. The other substances in the air are gases, vapors, and solid particles. Of these, by much of the most important is the vapor of water, which is always present, but in very variable amount according to temperature. It is by this vapor, together with carbon dioxide and suspended dust particles, that the radiant heat in the atmosphere is absorbed. The water vapor condenses into dew, rain, hail, and snow, and is thus of paramount importance in the great series of surface agencies which play so large a part in the geological changes of the Earth. In analyzing the air carried down in solution in rainwater, the atmospheric gases, together with ammonia, nitric, sulfurous and sulfuric acids, chlorides, various salts, solid carbon, inorganic dust, and organic matter have been detected. The fine microscopic dust so abundant in the air is no doubt for the most part due to the action of wind in lifting up the finer particles of disintegrated rock on the surface of the land. As a geological agent, the atmosphere affects changes by the chemical reactions of its constituent gases and vapors, by its varying temperature, and by its motions. Rather less than 3/4 of the surface of the globe, or about 144,712,000 square miles, are covered by the irregular sheet of water known as the sea. Within the last few decades, much new light has been thrown upon the depths, temperatures, and biological conditions of the ocean basins, more particularly by the Lightning, Porcupine, Challenger, Tuscarora, Blake, Gazelle, and other expeditions fitted out by the British, American, German, Norwegian, and Swedish governments. The water of the ocean is distinguished from ordinary terrestrial waters by a higher specific gravity, and the presence of so large a population of saline ingredients as to impart a strongly salt taste. The average density of seawater is about 1.026, but it varies slightly in different parts even of the same ocean. The greater density of seawater depends, of course, upon the salts which it contains in solution. At an early period in the Earth's history, the water now forming the ocean, together with the rivers, lakes, and snowfields of the land, existed as vapor, in which were mingled many other gases and vapors, the whole forming a vast atmosphere surrounding the still intensely hot globe. Under the enormous pressure of the primeval atmosphere, the first condensed water might have had a temperature little below the critical one. In condensing, it would carry down with it many substances in solution. The salts now present in the seawater are to be regarded as particularly derived from the primeval constitution of the sea, and thus it may be inferred that the sea has always been more or less saline. But it is manifest that, whatever may have been the original composition of the oceans, they have for a vast section of geological time been constantly receiving mineral matter in solution from the land. Every spring, brook, and river removes various salts from the rocks over which it moves, and these substances, thus dissolved, eventually find their way into the sea. Consequently, seawater ought to contain more or less traceable proportions of every substance which the terrestrial waters can remove from the land. In short, of probably every element present in the outer shell of the globe, for there seems to be no constituent of the earth which may not, under certain circumstances, be held in solution in water. The average proportion of saline constituents in the water of the great oceans far from land is about 3.5 parts in every 100 of water, and the proportions of the different chemical elements in the composition of the waters of the ocean as a whole are much as follows. Oxygen, 85.79, hydrogen, 10.67, chlorine, 2.67, sodium, 1.14, magnesium, 0.14, calcium, 0.05, potassium, 0.04, sulfur, 0.09, bromine, 0.008, and carbon, 0.002. Within the atmospheric and oceanic envelopes lies the inner solid globe, the only portion of it which, rising above the sea, is visible to man, and forms what is termed land, occupies rather more than 1/4 of the total superficies of the globe, or about 55 million square miles. It was formerly the prevalent belief that the exterior and interior of the globe differ from each other to such an extent that, while the outer parts are cool and solid, the vastly more enormous inner intensely hot part is more or less completely liquid. Hence the term crust is applied to the external rind in the usual sense of that word. This crust was variously computed to be 10, 15, 20, or more miles in thickness. The Earth's crust is composed of mineral matter in various aggregates included under the general term rock. A rock may be defined as a mass of matter composed of one or more simple minerals, having usually a variable chemical composition with no necessarily symmetrical external form, and ranging in cohesion from mere loose debris up to the most compact stone. Granite, lava, sandstone, limestone, gravel, sand, mud, soil, marl, and peat are all recognized in a geological sense as rocks. Direct acquaintance with the chemical constitution of the globe must obviously be limited to that of the crust, though by inference it may be possible eventually to reach highly probable conclusions regarding the constitution of the interior. Chemical research has discovered that some 75 simple or as yet undecomposable bodies called elements in various proportions and compounds constitute the accessible part of the crust. Of these, however, the great majority are comparatively of rare occurrence. The crust is mainly built up of about 20 elements, which may be arranged in two groups, metalloids and metals. Of the metalloids, oxygen and silicon represent 75% of the matter in the world, hydrogen, carbon, phosphorus, sulfur, chlorine, fluorine, and nitrogen being less than 1.5% altogether. While among the metals, aluminum is 7.45%, iron 4.2%, calcium 3.25%, magnesium 2.35%, potassium 2.35%, sodium 2.40%, and titanium, manganese, beryllium, barium, strontium, chromium, nickel, and lithium together are less than 1/2%. Of the other elements, upwards of 50 in number, the proportions are so small that probably not one of them equals as much as 1/100% of the whole crust. Yet they include gold, silver, copper, tin, lead, and the other useful metals, iron excepted. It will be observed that of the accessible part of the globe, over 3/4 consist of metalloids and less than 1/4 of metals. It is also interesting to note that 97% of the crust is made up of the 10 most abundant elements, that is, of the 3 first metalloids and the 7 first metals. Silicon is never found free, but always combined with oxygen. Comparatively, few of the elements occur free, but occur in more or less complex compounds with one or more others. The combinations which enter most largely into the composition of the Earth's crust can be determined from the collation of a sufficiently large number of chemical analyses of the more representative rocks of the Earth's crust. Such a determination has been made by Mr. F. W. Clark from the mean of 830 analyses of typical samples from the older or primitive part of the crust, and is expressed. The following are the chief: silica 59.71%, alumina 15.41%, ferric oxide 2.63%, ferrous oxide 3.52%, lime 4.90%, magnesia 4.36%, potash 2.80%, soda 3.55%, water 1.52%, titanic acid 0.60%, and phosphoric acid 0.22. In a broad view of the arrangement of the chemical elements in the external crust, the speculation of Durocher may be noticed here. He regarded all rocks as referable to two layers or magmas coexisting in the Earth's crust, the one beneath the other, according to their specific gravities. The upper or outer shell, which he termed the acid or siliceous magma, contains an excess of silica and has a mean density of 2.65. The lower or inner shell, which he called the basic magma, has from 6 to 8 times more of the earthly bases and iron oxides, with a mean density of 2.96. To the former, he assigned the early plutonic rocks, granite, felsite, etc., with the more recent trachytes. To the latter, he relegated all the heavy lavas, basalts, and diorites. The rocks of the Earth's crust are made up of compounds of the elements which have just been mentioned. These compounds geologists call minerals. Scott, in his Introduction to Geology, defines a mineral as a natural, inorganic substance which has a homogeneous structure, definite chemical composition and physical properties, and usually a definite crystal form. The number of known minerals is large and constantly increasing, but only a few enter in any important way into the constitution of the Earth's crust. End of section 11.